AP Calculus AB, Unit 6, Day 4 lesson. We're going to learn add some new derivatives to our list of derivatives. Okay. And we'll try and kind of derive them a little bit at first, just to give you some confidence using the definition of the derivative that we've learned. So let's see if we can figure out the derivatives of logs. So we'll just start with natural log. So I'm going to take kind of a graphical approach first. And so I'm just going to sketch the graph. So we know that natural logs are the inverse of exponentials. So we can start with that. And they have a horizontal asymptote, 0, 1, and then we're going to reflect it across y equals x. So 0, 1 becomes 1, 0. Horizontal asymptote, y equals 0 becomes x equals 0. Everything that's x becomes y. And so this is the graph we're looking at, right? And so let's see if we can sketch the derivative of this graph, something that we've done before. Can we sketch the derivative? What are some of the... So I want you guys to help me kind of figure out, okay, so like anyone see anything that really kind of sticks out about this graph's slopes that you think that, should be on there? So try and sketch the derivative graph here. So what are things about the derivative that stand out to you? I think one of the things I notice is that the slopes are all positive, right? All positive slopes. So that means this derivative graph is going to be above the x-axis the whole time, right? As we, let's see, as we're getting closer, let's see, it seems like as x goes to infinity, the slope is getting flatter, right? Less and less steep. So it's going towards 0, eventually. It's getting less and less the whole time. I mean, it's going up, right? The graph's going up, but the slope is getting less and less steep. As x goes towards 0, the slope gets infinitely steep, right? Right here, it gets super steep. So, how could we now? So I would say if the slopes are going towards 0, there's probably like a horizontal asymptote. The slopes are getting closer and closer to 0. As you get close to 0, it blows up. So probably like a vertical asymptote, right? And then in between, they're always positive. So it's getting super steep and it's getting closer and closer to 0. So maybe something roughly like that might be like the derivative. Now, it doesn't exist over here, but I mean, what does this graph look like? Does this graph look like any kind of function that we've studied at all? Vertical asymptote, horizontal asymptote. I mean, it kind of makes me think like rational functions, like where they might have something over here too. And, so the graph, looks like, the right half of like a really basic rational function, y equals 1 over x, right? Right, just the right half. So let's stick with that for a second. Let's see if we can take a different approach to kind of prove it. Now that was a natural log, but logs are probably the same. Natural log and logs are probably the same, but with maybe some little minor things, details for the natural logs would be a little different. So let's go and start with the definition of derivative. Okay, I'm going to do it for any log, any base. Okay, and we could have done all this stuff for regular logs. So here's the strategy we're going to take. This is, by the way, this is the difference quotient. This is the definition of the derivative. It's really just the slope, rise over run, between 2 points nearby, and then we shrink the run to 0, and it should approach the right answer. Now, if we use log rules, we could combine these two logs into one by dividing, right? If you have two logs, the same base, subtract, then you divide the second one into the first one. And we could, simplify this. 1 plus h over x. We could distribute the division. Now, I'm going to do something a little creative here. So far, everything's been kind of straightforward. I mean, using log rules maybe is a little creative, but I want to do something that'll help us see what's going on. Let's introduce a new variable, v, which is h over x. And therefore, h, so we're going to replace that with a v, but then we have an h over here, so h is going to equal vx. So whenever you write this, I replace h with vx, and I replace h over x with v, okay? Now, we got to change these limits too, because I got rid of all the h's, right? So the limit as h goes to 0 is going to translate to the limit as v goes to 0, right? Because as v goes to 0, h goes to 0. So we're going to change these to v. Because I replaced all the h's with this v, okay? Now, we're going to go ahead and use another log rule and bring this inside as an exponent, but just the 1 over v part. We're going to leave the 1 over x part. So we're going to bring the 1 over v right here, okay? And we're going to investigate what happens with this function. We'll use a graphing calculator to help us. Limit as v goes to 0 of just this part right here, of 1 plus v to the 1 over v. So we know that limits, we can take the limit of what's inside and then take the log of it afterwards. But let's see what happens with this. I'm going to use my graphing calculator. I'm going to show on my graphing calculator, I'm going to use a table function to just punch a bunch of different values in. So if I go to table, now maybe I could go to y equals first and put this in parentheses 1 plus, I'm putting x's in, raised to the parentheses 1 over x. Okay, so that looks right. I'm going to go to the table, and there's some other numbers already in there, and I want to see what happens as we get, we could just delete what's there. I want to see what happens. Remember, on table set, make sure independence on ask and dependence on auto. Otherwise, it's just going to fill the table in for you. You're not going to be able to choose what goes in there. Okay. So, we want x or v to be getting closer and closer to 0. We could start at 1, and that's what the answer is. We could start, and then we could go to 0.1. So if we start at 1, we get 2. If we do 0.1, we get 2.5937. 0.01, we get 2.7048. 0.001, we get 2.7169. 0.0001, we get 2.7181. Now, what does that number look like it's going towards? Like, as we get closer to 0, it looks like it's starting to settle in on some number, right? 2.71, and it's getting just more and more accurate. But what's happening here is that this is going, as the closer we get to 0, this is going towards e, the natural number e, which is kind of interesting. So this equals e. Kind of interesting result. So if we go ahead and we put that in there, say, okay, well, this is 1 over x log base b of e. And then I'm going to use another log rule called the change of base formula, change of base. So change of base lets you change a log from one base to any other base that you want. So log base b of e, I want to change it to natural log of base e, because I have an e in here. So it seems like it'll clean up nice. So we could do the new log of what was inside over the new log of what the old base was. That's the change of base formula. Okay. Now, natural log of, so that's what this right here will equal natural log of e over natural log of b if we choose to change the base e. Natural log of e is 1, right? And so we get 1 over x times 1 over natural log of b. So the derivative, there it is. That's the rule right here. The derivative of any log with any base is going to be 1 over x times 1 over natural log of b. In fact, we usually just combine it into 1. We just say 1 over x natural log of b. So we actually just developed it. Now, that's for any base. For natural logs, the base is e, right? So that means you're going to get natural log of e, which is 1. So it just becomes 1 over x, right? Because b equals e, and natural log of e is 1. So we get 1 over x. Hey, that's what we were saying it looked like. So yeah, the derivative of natural log is 1 over x. Kind of crazy. It's 1 over x. Derivative of natural log is 1 over x. Now, derivative of other logs has extra log of whatever the base is built into it. Okay. We use this one a lot more though. So in general, if we kind of want to build it in with like the chain rule, building in with chain rule, meaning we expect the inside of the log or natural log to be more complicated than just an x. So it's going to be 1 over what's inside, followed up with the derivative of what's inside, right? Chain rule. The derivative of what's inside, natural log of the base, times the derivative of what's inside. Okay, so just kind of illustrating that. Okay, so let's try some examples here. Find the derivative of the following. So this is going to be, we're going to have to do chain rule, right? And so this is like the u. I don't usually write it as u and all that stuff. I say, okay, well, derivative of natural log is 1 over what's inside. I don't think it was 1 over x. I think 1 over what's inside and then times the derivative of what's inside would be cosine x. Now, it doesn't end up in the bottom. It multiplies the whole thing. Your final answer, nicest form, cosine over sine, would be cotangent x. Okay? Let's try the next one. So you have an inner function, right? So we can do y prime equals 1 over what's inside, but you also need the natural log of the base, because this one's not, doesn't have any, times the derivative of what's inside, 3x squared. The natural log of 2 isn't part of that. Derivative of what was inside originally. So of course we want to clean it up. Rules of exponents, we could say this is 3 over x natural log 2. 3 over x natural log 2. Now, let's figure out what the derivatives of exponentials are. I feel like we kind of went backwards. We usually like to work with exponentials first and then logs, but whatever, we change it up. So exponentials. So let's take a graphical approach first, okay? So exponentials are the buddies of logs, right? So I bet there's some connections here, but we could just start with like a graphical approach of an exponential, right? So let's see if we can sketch the derivative. So if we sketch it, the derivative, slopes are getting flatter and flatter as they approach the horizontal asymptote. So I bet this one has a horizontal asymptote also. So anytime a graph has a horizontal asymptote, there's going to be some kind of horizontal asymptote in the derivative graph going to 0 for sure. So we get a horizontal asymptote. As it gets smaller, it gets smaller. As the graph gets bigger, it just the slope keeps getting steeper, right? I mean, so all the slopes are positive, right? Kind of an observation that we made. Same. Um, as x goes to 0, the slope goes to 0. As x goes to negative infinity, the slope goes to 0. As x goes to positive infinity, the slope goes to positive infinity. It just keeps blowing up, getting steeper and steeper. So it kind of looks like probably like this. It goes over here towards 0, and then it keeps getting bigger and bigger and bigger. Okay, what graph does that look like? It looks really familiar. Man, I feel like I've just seen that graph before. Something that looks really close to it. Oh, wait, that looks a lot like its own graph, its original graph. Well, let's see. So, I mean, right now, looks like y equals e to the x itself, its original graph. Let's see if we can prove it, okay, in a little more way. Now, this proof is going to be a little different kind of proof. Instead of using the definition of derivative, I'm going to use the derivative for natural log, which we already proved. Okay, so we're going to go ahead and take advantage of that. I'm going to take the natural log of both sides. Okay, which is going to give you natural log of y equals x, because natural logs and exponentials are inverse functions, right? They cancel each other out. What would you raise e to get e to the x? Then I'm going to take the derivative of this implicitly. So the derivative natural log of y is 1 over y. That's the rule that we proved on the front, right? Derivative natural log is 1 over what's inside. But then you got to multiply by the derivative of what's inside, dy dx. Because we want the derivative with respect to x. The derivative of x on the other side is just 1, right? If you were to solve now for dy dx, we get dy dx equals y, which is e to the x. Right? Y is e to the x. So we've just proven that the derivative of e to the x is e to the x. It's itself. This is the only function that is its own derivative, except for if the function was 0, then I guess the derivative would be 0. But that's like boring, dumb. We're not going to encounter functions that are 0. So this is kind of crazy. So derivative of e to the x is e to the x. Okay, and then sort of with the chain rule, you could say the derivative of e to something is e to something times the derivative of what's inside. Okay, now that's e. That's a specific exponential. What if it has a base other than e? What is the derivative? Well, you can guess it's probably a lot like that. It is itself. Okay, but then it has an extra natural log of the base. So very similar to the logs with any base. They were 1 over what was inside with the natural log of the base in the bottom. This also has the natural log of the base. So that's in general. But we use this one a lot. We encounter the e to the x one a lot more than this, which makes these hard to remember because we don't see them that often. But they do. This is a special case of this, because if the base is e, natural log of e is 1, and you just get itself. Okay, so today's assignment, out of the book, all odds, check them all in the back of your book, 267, 1 to 35 odd. Let's get some practice using these rules. This might seem like a nice break after all these related rates problems, which are pretty crazy, long, and complicated. This is a little more just simple, apply the rule, repeat. So here you go. Try it out.